Hi, I'm Chong Wei from the University of Utah. My research makes parallel computing easier to handle so you can quickly boost your application performance. Today, I'm going to show you Taskflow, an open source C++ programming system that can help you quickly write parallel CAD application. You probably already know parallel computing is critical to advance your CAD tool performance. For example, a single-threaded timing analysis program can take several hours to finish, but it can be reduced to only a few minutes or even a few seconds if we are able to run it in parallel. That's the power of parallel computing. By leveraging many core processing units, we are able to speed up the performance by several orders of magnitude. However, writing a good parallel program is very challenging because you need to deal with many technical, difficult details, such as standard concurrency control, task dependencies, scheduling, and data rates. Many developers have hard time in getting them right. This problem is indeed more serious in CAD application because CAD deals with some of the most challenging computational problems in the world. For example, the layout generation process requires a partitioning graph of billions of nodes, floor plan, placement, placing millions of cells in a small area, routing trillions of wires to establish a signal connection, and finally, we analyze the timing of these billions of components. The resulting task computational graph in terms of encapsulated function code and task dependencies can easily go up to millions of tasks with cycle, dynamic control flow, and irregular computational pattern that takes several days to finish. Taskflow offers a solution to this. We address the following question. How can we make it easier for CAD developers to quickly write parallel and heterogeneous programs with high performance scalability and simultaneous high productivity? By high performance, we mean the program runs fast and scales to many core processing units, including CPU and GPU. By high productivity, we reduce the time it takes to implement the program. Let's take a look at Hello World example in Taskflow. Suppose we want to do 4 things, A, B, C, D, each representing a function or a task. A has to run before B and C, and D has to run after B and C. When A finishes, B and C can run in parallel. When both B and C finish, D can start. This is how it looks in Taskflow. Only 15 lines of code to get a parallel task execution. This is all you need. You create a Taskflow object to manage your task dependency graph, and then you create an executor that manages a set of worker threads to run Taskflow. Here we use emplace method to create 4 tasks in terms of C++ lambda and assign it to A, B, C, D using structure binding in C++ 17. To build up a dependency, we use precede method to force A to run before B and C, and use succeed method to force D to run after B and C. Finally, we submit this Taskflow to the executor, and it returns a future where we can wait on it to finish. At this moment, I believe many of you can fully understand what this code is doing. The code explains itself through an expressive graph description model. Here is what I'm going to do in the rest of the talk. I'm going to show you how to express the parallelism in the right way by starting with the motivation behind Taskflow and the applications we target. Then, I will present how to use Taskflow to parallelize your application so you can quickly leverage Taskflow to your job right after the presentation. Next, I will demonstrate some real use cases of Taskflow and show you how it can boost performance in large-scale parallel application. Let's start with number 1, express your parallelism in the right way. Over the past years, we have invested a lot in existing parallel computing systems to assist us with the implementation and deployment of parallel CAD algorithms. These systems include pthread, OpenMP, C++ thread, Intel TPP library, HPX, StarPU, and lot of software from the Exascale Computing Project, led by Department of Energy, such as COCOS and Parsec. Unfortunately, we found few of them can meet our purpose. because these systems are not fundamentally designed with the unique parallelization challenges of CAD. We summarize two big problems. First of all, CAD defines very complex task dependencies. For example, analysis program needs to compute a circuit network of billions of nodes and dependencies. That is, the resulting task graph in terms of model function call and their dependencies can go irregular in millions. And the problem is, most existing tools are good at do parallelism, but they are not very strong in expressing heterogeneous task graph at this large scale. For example, OpenMP is very good at regular parallel for do, but it's not very efficient for irregular task parallelism. Second, our problem defines very complex control flow. For example, optimization algorithms make essential use of dynamic control flow to implement various computational patterns to carry out combinatorial optimization and analytical methods. And the problem is, most of the existing tools require you to describe a parallel workload in a directly acidic graph, and they do not anticipate cycles or conditional dependency. And the result of that is lacking end-to-end parallelism because you need to partition your workload or algorithm across the control flow decision-making point, and you synchronize your parallelism at that decision-making point. After several years of research, we arrived at a key conclusion. We need a new C++ parallel programming system to help us parallelize CAD. And the takeaway here is, while designing parallel CAD algorithm is non-trivial, what makes parallel CAD an enormous challenge is the infrastructure work of how to efficiently express dependent tasks along with an algorithmic control flow and schedule them across heterogeneous computing resources. Therefore, I'm going to show you how we can use Taskflow to parallelize your application. Taskflow defines 5 task types: static tasks, dynamic tasks, cudaFlow tasks, condition tasks, and module tasks. Static task is the most basic task type in Taskflow. It takes a callable object and runs it. A dynamic task lets you spawn a task dependency graph during the execution of a task so you can do dynamic parallelism. A cudaFlow task lets you describe a GPU workload in a task graph and offload it onto a GPU. A condition task lets you integrate control flow into a task graph so you can describe end-to-end parallelism without partitioning your parallelism across control flow decision-making point. A module task lets you compose a large task flow graph through smaller task flow that are easier to optimize. Because of the time limit, I'm not going to talk about all the 5 tasks. Instead, I'm going to focus on static tasks, cudaFlow tasks, and condition tasks. And you can find a tutorial for all these 5 tasks in our website. In the Hello World example we have seen before, the 4 tasks A, B, C, D are static tasks. They take 4 lambdas, C++ lambda, and run them. You can offload a task to GPU. We manage heterogeneous CPU-GPU tasking through a closure-based interface cudaFlow. A cudaFlow is a task associated with a CUDA graph, which is a new feature in NVIDIA since CUDA 10 on Turing architecture. A cudaFlow is very similar to dynamic tasking. It takes an argument of cudaFlow that will be created during execution of the cudaFlow task. Within this cudaFlow, you describe multiple GPU workload, such as data transfers, kernels in a task dependency graph, rather than aggregated operation such as that using cudaStream. In this case, we have 2 copy tasks that move data from X and Y from the CPU to GPU, and a kernel task that offloads a written sexcp kernel, single precision AX plus Y operation kernel to GPU. Another 2 copy tasks to get the data back from GPU to CPU. By leveraging the power of CUDA graph, we launch the entire GPU task graph in a single kernel call instead of multiple ones, so we can largely reduce the overhead. More importantly, when you finish the description of a GPU task graph, you can pipeline the entire cudaFlow with other CPU tasks or other cudaFlow. And this is very important because in many CPU GPU programming, they always involve some data transformation tasks at an expensive cost. Without a suitable task graph interface, it is very difficult to express this overlap that we can take the most advantage from CPU GPU programming. The design of CPU GPU heterogeneous tasking has three motivations. First, our closure enables stateful interface. You can capture data in reference to marshal data exchange between CPU and GPU tasks. This is important for graph parallelism because when everything is formulated as a task graph, we need to make sure the computation result of CPU tasks is visible to GPU tasks and vice versa. For example, CPU tasks compute the data size and then GPU tasks know how to set up the kernel parameter. Second, our closure interface can hide implementation detail judiciously. It provides a lightweight abstraction over GPU implementation. By default, we use cudaFlow because of its excellent performance. Also, this closure interface is extensible to new accelerator type. For example, we can define SQL flow, OpenCL flow, TPU flow, or FPGA flow. We can tailor a graph interface for each of the accelerator type. One thing I would like to highlight is, in Taskflow, we do not try to simplify kernel programming, but focus on CPU-GPU tasking that affects the performance to a large extent. The reason is the same for data extraction, so Taskflow can complement many of the existing kernel programming systems. Conditional tasking is a powerful interface to enable dynamic control flow, and we believe this is one of the key features that stands out Taskflow from the other libraries. You can create a condition task that returns a value indicating the next immediate successor to run. Let's take a look at an iterative optimization program, for example. I create a task graph of 4 tasks: init, optimizer, converge, and output. Init task initialize the data structure we need for optimization. Optimizer task launches the optimization routine, such as solving a linear system in a matrix form on the GPU. Converge task check if the optimization converges, and it forms a cycle back to the optimizer if we haven't reached a convergence point. Or moves on to the output task and stop. The converge task here is a condition task, and it precedes 2 tasks, optimizer and output. With this order, when it returns 0, the scheduler will re-execute the optimizer task again, or otherwise, it proceeds to output and stop. And we ask user to specify least condition in the return value of condition task. In this example, there are ultimately 4 tasks ever created. You describe this iterative workflow in the whole graph entity. There is no need to partition your graph and synchronize your parallelism at each control flow decision-making point. How do existing frameworks handle condition? Well, we know many of them are based on direct acidic graph, and they do not allow cycles. Here, I'm not talking about the cycle you have in pipeline, but a generic interface for you to describe control flow in a parallel task graph. The most common solution is to expand the task graph across fixed-length iteration. For example, if you happen to know a loop condition is going to span 5 iterations, you can unroll the task graph. The result of that is, of course, increased graph size and memory consumption. But what about a loop condition of unknown iterations, like non-deterministic conditions? No, in fact, according to our research, for generic conditions like this, existing frameworks suffer from exponential growth of coding complexity. The biggest advantage of Taskflow is everything is unified. You use the method in place to create a task, which can be either a static task, dynamic task, condition task, composition, or cudaFlow. Then you use the single method precede to relay a dependency between tasks. You can create a really complex graph that combines all the 5 task types and integrate control flow into your task flow, so everything runs end to end. And our scheduler will perform end-to-end optimization on the whole graph to optimize the runtime, energy efficiency, and throughput of executing your graph. We just learned the core programming models of Taskflow to describe a parallel program using a task dependency graph. Being a CAD developer, not only do we care about the expressivity of the library, we also need performance. I'm going to show you 2 applications we have successfully applied Taskflow to and the performance we have obtained. The first application is a VLSI placement workload we have applied Taskflow to solve. VLSI placement is a very important step in the circuit design flow. It optimizes the cell location on the chip. A cell is essentially a gate. It can be OR gate, NAND gate, NOR gate, and so on. In modern design, there are millions of cells in placement optimization that can take several hours to finish. The challenge is placement optimization makes essential use of dynamic control flow to describe iteration. To speed it up, we implement a GPU-accelerated algorithm in emplace that leverages cudaFlow to offload tasks to GPU and condition tasks to capture the iterative control flow. Here is a partial task flow graph of 4 cudaFlow. You can see we have 1 condition cycle and 12 static tasks to describe a tiny fraction of the graph, together with GPU using cudaFlow. Keep in mind, the entire graph is much larger than this. We compare the performance of Taskflow against TPP and StarPU, which are the 2 popular task programming libraries that have been used in CAD community. We measure the performance in terms of runtime, memory, and energy efficiency in these 3 figures. Blue line is Taskflow, red line is TPP, light blue is StarPU. On the top left figure, the runtime plot, you can see Taskflow is a bit faster, and the difference starts to increase when the program size becomes large compared to TPP and StarPU. All algorithms saturate at about 16 CPU core, but before that, we found Taskflow is always faster. We know this placement optimization workload is iterative, and we use condition tasks in Taskflow to model the dynamic control iterative flow. Because TPP and StarPU do not allow cycle, we flatten their task graph across the placement iteration found in hindsight. Result of that is increased memory, because they are invoking a much larger task graph that will otherwise be described in a simple condition loop if the programming model supports that. Running larger graph also causes higher energy consumption. And you can see in the power data, Taskflow is much more energy efficient than the others. Another important reason to this is our specialized work stealing scheduler that balances the worker and available task parallelism during the execution. Definitely check out our website to find out more details about our scheduling algorithm. The second experiment I'm going to demonstrate is a real application on machine learning. Here we try to compute the inference of a very large deep neural network. It has 1920 layers, each of 65536 neurons. The entire network can take up to 50 gigabyte memory. This is also the problem given by HPEC, High Performance and Extreme Computing Conference, as its yearly graph challenge problem. The figure here is a partial task flow graph of 4 cudaFlow, 6 static tasks, and 8 condition cycles for this machine learning workload. Each cudaFlow contains thousands of GPU tasks. If you launch these GPU operations one by one, the overhead is going to kill your performance. Because the network is very large, the advantage of task graph parallelism starts to come out. This slide shows the performance data where we compare Taskflow with TPP and StarPU again. This machine learning workload is iterative, so we use condition tests of Taskflow to model the control flow. However, TPP and StarPU do not support control flow, so we unroll layer task graph across iteration from in Python. And we implement cudaFlow graph for all the baseline. The figure in the middle shows the runtime and memory at different CPU and GPU numbers. Again, blue line is Taskflow, red line is TPP, light blue is StarPU. In general, you can see Taskflow is much faster than TPP and StarPU. It's about 2x faster. Memory is about 1.6 less because of the use of condition tests. There is no explicit synchronization of client-side partition across the control flow due to the use of condition tests as well. And one thing I would like to highlight is our solution just received a champion award from the IEEE MIT Amazon HPEC Graph Challenge in 2020. I would like to summarize this result with a key takeaway. Parallel programming infrastructure is just as important as the parallel solution itself. Different parallel programming models are going to give you different implementations. The parallel CAD algorithm itself may run very fast. However, the parallel computing infrastructure you use to support that algorithm may dominate the entire performance. This is especially important when you consider heterogeneous workload, because the control flow decision frequently happens at the boundary between CPU and GPU tasks. If you do not have a dedicated interface for expressing CPU-GPU dependent tasks, along with algorithmic control flow, the overhead to partition or synchronize your heterogeneous parallelism may outweigh its performance benefits. I would like to take this chance to say thank you to all the users. There are many people using Taskflow right now. I'm very grateful for the tremendously useful feedback from users. I'm very open to collaboration, whether you are interested in using Taskflow, understanding more technical details, or getting me to give a talk in your organization so we can talk about how Taskflow can help you boost application performance in your application. Go visit the link below to the project and you will be able to find more details about the project. Thank you very much.